Okay, quick outline. So first I'll discuss briefly where the intersection of nuclear physics and astrophysics is, though most of you can probably get a good idea of that. Go into the Big Bang, a little bit about this lithium-7 abundance problem, and spend the rest of my talk kind of discussing this and how this experiment we did at Oak Ridge to look for the certain resonance enhancement of this reaction could resolve this problem that they were seeing in calculations. So, where does the intersection of nuclear physics and astrophysics come in? A lot of it comes in the origin of elements. So one of the big questions in science, or more specifically in astrophysics, is where did everything come from? How did lithium form? How did all the heavy elements form? All the medium mass elements form? What happened in the Big Bang? You know, what elements were formed then? We know fusion occurs in stars. So, but what kind of fusion? What other processes might be occurring? You know, what different types of burning are occurring in stars that could produce these heavier elements? What about the really heavy elements? Where are those coming from? You've probably heard this phrase, R process, thrown out a few times, which is basically this series of rapid neutron captures. So these stable isotopes are capturing these neutrons really rapidly, and then you get this chain of captures and decays up the neutron-rich side of the table of isotopes. And then there's the RP process, which is kind of the same thing on the proton-rich side. But again, where do these processes happen? What reactions govern this? So this is the kind of thing that nuclear physicists interested in astrophysics, these are the kind of questions they tend to answer. But I like to start, when I'm discussing nuclear astrophysics, I like to start from the very beginning. So you guys, most of you at least know something about the Big Bang, but I'd like to take a little time to go through some of the, I guess, slightly finer details of it. So the theory of the Big Bang has been around for a long time. It was proposed back in the 40s to explain the origin of the universe. Initially, it says that the universe initially starts as this very hot, dense gas. It's about the size of an atom, as it turns out. And then for some reason, no one really knows why, it starts expanding. All right, so the universe starts expanding, and as it expands, it cools. And around 10 to the minus 32 seconds, this dense plasma of something, we're not really sure exactly, no one's really sure exactly what was going on, cools enough so that you actually get this soup of electrons and like quark-antiquark pairs. Now, around this time, you've actually got this balance between matter and antimatter. But something happens, again, shortly after this, and no one's really sure quite what happens, but you get this instability occurs, and you start getting a lot more matter than antimatter, which is why the universe exists the way it does now. But exactly what process governs this, no one's really quite sure. So the universe continues to expand, it continues to cool, which is important because eventually it cools enough so these quarks can bond and form heavier, more composite particles, protons, neutrons, other kind of composite quark particles, leptons. And again, the universe continues expanding some more. And after around 1 second, this phase starts called this nucleosynthesis stage starts. Now, all this really means is that the universe is cooled enough that the protons and neutrons can bond to form more heavier elements. So you got your helium, you get your lithium going. And this lasts anywhere between 3 minutes to 10 minutes, depending on which model you're actually using for this. And then afterwards, the universe cools too much for the particles to overcome the Coulomb barrier. So this stage of nucleosynthesis kind of ends. And then the universe continues to expand some more. Now, throughout all this time, all these particles are in this, I guess you can call it like a background, this soup almost of electromagnetic radiation. That's, whose wavelength is tuned to the temperature of the medium. And so as the universe is cooling, the wavelength is increasing, energy of this background radiation is dropping. And after about a few 100,000 years, this radiation is too low in energy to actually prevent the electrons from bonding to the atoms, so it actually decouples completely. And then you get state neutral atoms forming. So you get your hydrogen atoms, your helium atoms forming, all the electrons are bonding. Universe continues to expand some more, and then eventually you get stars forming, and then galaxies forming, and then here we are today discussing it. So what kind of evidence seems to support the Big Bang? Well, for starters, the universe does exist. We know this because we're here now discussing it. So that's one pillar to support the Big Bang model. There's Hubble's law, which most of you guys have heard about, which basically says galaxies are moving away from us at speeds that are proportional to the distance from us. So, and we've, Hubble's telescope has shown this, hence the name Hubble's law. And then there's this cosmic microwave background, which again most of you have probably heard of, which is from, as I mentioned before, around a few 100,000 years after the Big Bang, radiation completely decouples from matter. But it didn't go anywhere, it was still there. And as the universe kept expanding, it kept cooling to around this 2.7 Kelvin temperature. And this we've been studying for a long time. So this is one of the biggest supports for the Big Bang model. Now, so what goes into these Big Bang models? Most specifically, I'm actually going to spend most of the rest of the talk discussing this period right around here, around 1 second to a few minutes after the Big Bang, where this period of nucleosynthesis occurs, where all these light elements are forming. So what goes into models that try to understand what goes on in this period? Well, you get your standard model of particle physics, sure. You get general relativity, and I'm not an expert in this, so don't ask me any questions about general relativity. And then, of course, most important for people like myself or nuclear experimentalists are these nuclear cross-sections, stuff that we can actually measure in a lab. And all this goes into this model to produce these light elements that are seen in the Big Bang. Now, the way it works out is all of this turns out to be a function of one single parameter, the baryon density of the universe, often listed as this eta parameter, this baryon to photon ratio. So the goals of science, the goals of these Big Bang model people, I guess, scientists, are to determine what this eta parameter is, make astronomical observations so they can compare their model calculations to something real, so they can test their models. There we go. So what kind of basic reactions occur in these things? So this is just like the simplest reaction networks that they see in these nucleosynthesis models they use. And it's really just a series of simple reactions. You get, proton capturing a neutron becoming a deuterium. You get, tritium interacting with an alpha to form, I think I'm losing my laser. There we go. Yep. There we go, to form lithium, just basic reactions like this. And these cross-sections are often measured in a lab experimentally. Energy is around 100 keV. Now, the more challenging part, at least I thought the more challenging part, is actually in these observations. So how do you make observations of abundances, so concentrations of elements from the Big Bang? I mean, that's millions of years ago. It's really difficult to do. So what they do is they look for stars. It's done slightly differently for different isotopes. But for lithium, which I'm going to focus on for the remainder of my talk, they actually look for stars that have a low metallicity content. Now, when astrophysicists talk about metallicity, they refer to how much metal the star has. And when they say metal, they're really referring to just heavy isotopes, anything heavier than helium, generally. So when they discuss a star, they talk about the hydrogen density, the helium density, and then everything else, often. So stars with a low metallicity tend to be stars that form from gases that are kind of representative of the primordial gases of the universe, because there wasn't really anything in those gases after the Big Bang other than the really light elements. So they look for these population stars, 2 stars, and they look for this 670.7 nanometer line that's characteristic of atomic lithium. Now, as it turns out, this is actually a doublet, not a singlet, because in stars you see lithium-6 and lithium-7. And because of the difference in neutron number, the charge density in the nucleus is slightly different, which then affects the atomic orbitals just a little bit, just enough so that these lines are very slightly separated. Well, sometimes. But we know where these lines should appear, so we're actually able to use where the centroid is in these peaks, where the centroid is, we can fit that, and that tells us how much of this doublet peak consists of which isotope. So we're actually able to do a really good, or a pretty good extrapolation of the lithium-6 and lithium-7 abundances from these stars. And what they do is they do this for a whole range of stars of different metallicities, and they fit this data and extrapolate to 0 metallicities. That should be the Big Bang lithium-7. And they use this as their early universe fit for the lithium-7, or early universe calculation, or measurement, if you will, for the lithium-7 abundance. So, of course, the next stage is to actually compare this to a model calculation. So, as I said before, most of the models, the abundances are all a function of this one free parameter, this eta parameter, this baryon density. Actually, measuring this was proved to be very challenging until about 10 years ago when this deep space probe, WMAP, was released. And what among many things it did, it measured fluctuations in the cosmic microwave background. And men more clever than myself were able to use this and extrapolate a really precise measure for the baryon density parameter, this eta parameter right here. So rather than being in this long range, it's actually measured to be about 6.23 with this error bar here. And with this precise measure for eta, they're able to do much more precise calculations for these Big Bang abundances. Now, this chart is very busy, but it's not too complicated. Let me just walk you through it. So you see these darker curves here. These represent Big Bang model calculations done as a function of this eta parameter. So this is eta, and these are abundances, usually done relative to hydrogen, because that's something we understand well. These vertical bars that you see actually represent the measured abundances done using techniques I described in the previous slide, done by different astronomers. And this vertical bar here is actually WMAP's measure for the eta parameter. So where this bar crosses the curve would represent the prediction for the Big Bang abundance of that isotope. So as you see for helium, deuterium, isotopes, even hydrogen, as it turns out, you actually get really good agreement between model predictions and observations. But when you look at the lithium-7 line, there's actually this, you see this big discrepancy here between this bar and where the yellow bar here crosses the curve. And if you look at the numbers, it actually works out to be a factor difference of 3 to 4. Now, this number varies just a little bit depending on who does the calculation, but mostly it comes out to be about a factor of 4 different. And currently, this is not well understood why this is the case. Many explanations have been proposed over the years. Maybe something, there's some reaction happening after the Big Bang nucleosynthesis that we're not taking into account that's actually destroying lithium-7. Maybe there's some new physics that we don't know about that was more strongly occurring in the early universe. But again, for people like myself, or nuclear experimentalists, we're more interested in what kind of nuclear physics solutions could exist. So what they do is, I showed you that series of reactions, there's 11 cross-sections that people measure in a lab, and maybe there's some kind of enhancement of those reactions that we haven't previously seen before. So many resonances were proposed and were searched for over the years after WMAP. And then, so new models trying to resolve this discrepancy had a much more extensive network, as you can see, much more reactions occurring here, along with the ones that we saw before. But I want to focus more on this region here, where you see all these reactions involving beryllium-7. Now, why do we care about what happens to beryllium-7 when we're actually interested in a lithium-7 abundance issue? Well, it turns out that most of the lithium-7 in the Big Bang is produced as beryllium-7, because beryllium-7 is easier to make, since it's basically a helium-3 bonding with a helium-4 rather than a tritium atom. And then this beryllium-7 has a short half-life, a couple of months, and it beta decays into lithium-7. That's where they believe most of the lithium-7 occurred. So the idea is, if we're destroying beryllium-7 before it has a chance to decay, then that could explain why we're not seeing as much lithium-7 as we might expect to see in the Big Bang. And okay, so there's one particular reaction. So it's been thought that if a deuteron, one of the many reactions that occur in the Big Bang is deuteron capturing on beryllium-7 and destroying it. And it's thought there might be some resonant state. Now, when they talk about a resonant state, they mean the deuteron comes in, and instead of going through like a bound state, it actually goes to a state that's above the binding energy. So it's actually an unbound state in the continuum. So the reaction actually goes through this state, and it doesn't bond, but because there's, the energies are favorable, there's an enhancement to the reaction cross-section. So an enhancement to the probability of an interaction occurring. So they think there might be a resonance there around at an excitation energy at 16.7 MeV. And the reason they believe this exists is if they look in the mirror nucleus, lithium-9, or lithium-7 capturing deuterium, there actually is a resonance enhancement there. So they thought that might exist. And the way the kinematics works out, if you look for, if this resonance exists, to solve the problem, it would have to be between it would have to be around 200 keV and have a width of 30 keV. Now, don't worry about what a resonance width actually means. It's like a whole talk to go into this, but these are just two characteristics of a resonance. And if it was going to resolve this discrepancy, it would have to have these parameters. So beryllium-7 is a very popular nucleus, as maybe you might know. So it's been studied extensively over the years. And actually, this deuteron capture on beryllium-7 was studied by this group several years ago. But several papers came out kind of questioning some of the assumptions they made in their analysis. But again, I'm not even going to talk about that, because the most important part about this is that the protons they were looking for from this reaction, the outgoing particles, were very high in energy, and any kind of any particle coming from this state would have been very low in energy. So they wouldn't have seen it anyway, even if they had been looking for it, they wouldn't have seen it. So and this discussion about this one resonance, because it was the last nuclear physics solution that could exist for this lithium-7 abundance problem, had been discussed over and over again at conferences, and I actually heard a couple of heated debates about this, and I'm like, guys, it's just a reaction. But so at Oak Ridge, we realized that, hey, we can do this measurement very easily, just elastic scattering off deuteron, because elastic scattering is just the deuteron comes in, hits the beryllium-7, and that same deuteron comes out. But you can scatter through these unbound states. So if a resonance existed for the deuteron coming in this unbound state, then you would see it in the outgoing cross-section. You would see it in the cross-section, some kind of enhancement, if there was such a resonance to capture there. So we actually do this measurement at Oak Ridge. So just to show you a brief schematic of the facility. Right here, actually I think it's actually over here, so my arrow is wrong, but there's this cesium cathode where they take this beryllium-7 pellet, they stick it in, and I won't go into the details, but essentially they spallate the beryllium-7 off the pellet and inject it into this beamline. At this point, it's got a negative ion, which is very important for how this tandem accelerator works. So it's positively charged up here, so this negative ion gets accelerated to the top, and there's this foil there. And as the beam passes through the foil, it strips off some electrons, making it positively charged, and then it accelerates down the other side, and then gets delivered to our setup. So we had a really simple setup. We just had at forward angles. We had this silicon detector, this annular silicon detector. Basically, it looks like a CD that's segmented into strips, each strip representing a different theta angle. We had a CD2 target, which is basically deuterated plastic. So instead of hydrogen in the bonds, you've got deuterium, because chemically they react very similar. And then downstream, we had an ionization chamber to monitor the status of our beam. Now, as I said, the resonance we're looking for was at 200 keV, which in center mass, which in the lab frame turns out to be about 900 keV. Now, those who work in accelerator physics know it's really difficult to get a beam of particles at 900 keV. So what we actually do is we get a beam of 10 MeV, and we have a really thick target. What we want to do is if we stop the beam in the target, then as it's slowing down, it gets to the 900 keV energy range we're interested in. And then the outgoing particles would still react at that point, and we might still see deuterons coming from that. Now, the challenge of this, as I said, is any kind of the deuterons coming from this resonance will be very low in energy, and this is the thick target. So energy loss of the deuteron in the target is a problem. So what we want to do, ideally, is stop the beam at the very back of the target, but that's not always easy to plan in advance. So what we did is we made a thinner CD2 target that would slow the beam down a lot, but wouldn't quite stop it by itself. And then we rotated the target, which would increase the effective target thickness. And we rotated it up to the point where we stopped seeing beam in our ion chamber, which we believe was the point where the beam was stopped at the back of the target. And then I did some kinematics calculations too. This turned out to be about 50 degrees. I did some calculations to show that that's about where we expected it to be anyway. So at this point, the beam's stopping at the back of the target, so outgoing deuteron should be able to get out of the target and not be lost. Now, another reason we used our ion chamber, now as I said, beryllium-7 decays into lithium-7. That's why we're interested in it. But of course, in our experiment, we had a mixture of beryllium-7 and lithium-7 in our beam. Now, all we see is an outgoing deuteron. We don't actually see anything else. So it's really difficult to determine whether that deuteron came from a beryllium-7 reaction or a lithium-7 reaction without anything else detected. So as I said, now we had the stripping foil at the top of our tandem, which strip off some of the electrons. Now what you do is, it doesn't just strip off one electron or two electrons, it creates a distribution. And then you tune your accelerator to pick out the distribution you're interested in. So what we did is we tuned we didn't, but the operators tuned the accelerator to pick out a charge state 4, so it's fully stripped, there are no electrons. And we know a charge state 4 is a nice charge state for beryllium-7 because lithium-7 doesn't have a charge state 4 because it's only got 3 protons. So as you see, we also had a very nice clean beam. What this does, it also lowers our beam rate, but we had a pure beam, which was more important for us in our case. So pure beam of lithium-7, or beryllium-7. To analyze this, to analyze this, we use this R matrix code, and apparently I'm slightly running out of time, so I'm actually just going to gloss over this real quickly. Basically, this is an overly simplified version of the R matrix theory. Now, basically divides space into 2 regions, this internal and external region. The external region consists of your long-term forces, so the Coulomb interaction basically, and that's a reaction that's well understood, and the wave function is approximated as asymptotic form, so that's well understood. And the internal region is the more complicated nuclear reaction. And what you do is the internal region is a bound state, is a closed system, so the eigenstates form discrete bases. You expand your outgoing wave function in terms of the ingoing, in terms of these eigenstates, and then you equate them at the boundaries, and then you're able to use boundary conditions to solve the equation. And the R matrix actually takes into account all the non-diagonal components, all the complicated parts of the nuclear interaction. And this is overly simplified for the theorists in here, so I apologize for you. Okay, to do this, we actually, to do this analysis, we actually use this called multi, R matrix called multi. Now, we did a calculation right before the experiment to give us an idea of what we might expect to see. So this is the cross-section done as a function of the center of mass energy. And the parameter I put into this was basically right in the middle of that range we're looking for, so 200 keV resonance, a 30 keV width. And we might expect to see something in our data that looks something like this. See this little peak here, where this resonance would be if it existed. We're not sure, we were doing the measurement. And all this was done at 10 degrees, mostly because it's a representative angle. There's nothing special about 10 degrees, it's just a nice angle, and that's doing the talk based on this angle to be consistent. But when we actually look at the data, no resonance was very clear to us. Now again, this is actually in lab angle, so we'd actually be looking around, or lab energy, so we'd actually be looking at this region here. But maybe there's a little blip there, and it's not sure. But this is where we might expect the energy of this resonance to be if it existed. So, but this isn't the end of the story. This is just mostly raw data. Certain corrections have to be made. And I'm actually going to maybe skip over the corrections because mostly it's not very interesting anyway. But essentially, I had to take into account energy loss of the deuterons because we stopped the beam with the back to the target to minimize energy loss, but there was some energy loss in the end. So we took that into account using kinematics codes. Had to make certain corrections to the cross-section, which involved using SRIM to estimate a stopping power. And then, of course, I had to convert to the center of mass. And I'll just flip over here. OK. Now, so this is, again, the data again, now corrected. And I've got two multi-calculations here. One using a 0 keV width. So basically, it's Rutherford scattering, something that we all know very well from our undergraduate physics. And then the 30 keV resonance I showed before, just for a comparison. And it's not super clear based on this, but it does seem the data, there's no resonance seems very clear in the data. It does seem to follow the 0 width resonance, as Rutherford scattering, much more readily. But we can do a much better, instead of just saying the resonance exists, we can do a more thorough analysis. And again, I won't go into the extreme details of this, but mostly what we do is we can set an upper limit. So all we can really say is that we don't see a resonance. So our energy, all we can say is that our resolution was not sufficient enough to make out a resonance if it existed. But we can say that if the resonance existed, it would only it'd have to be at less than a certain width. So we can set an upper limit on what the resonance width would have been. And that turns out to be, as we do this for all the different angles, we actually get an average width of about 1 keV. So that's what you want to take out from this. You get an average upper limit of 1 keV. OK, now let's wrap this up and say, what does all this mean? OK, so to elaborate on, or restate what I said before, there was this lithium-7 mystery at Big Bang abundances. I'm not really sure what the solution was. It was proposed that there might be an enhancement of this deuteron capture on beryllium-7 could explain the problem. No resonance. So at Oak Ridge, we did this reaction on a thick target using a beam of beryllium-7. We did not observe a resonance, but we set an upper limit of 1 keV. Now, since we can't say the resonance it does exist, but with an upper limit of 1 keV, that's about a factor of 30 smaller than what it should have been in order to resolve the problem. So while we can't say if the resonance does exist, we can say if it does exist, it's too small to solve the discrepancy. So that was our conclusion in the end. So this solution that everyone was really thinking might solve the abundance problem doesn't actually solve the problem at all. So other solutions need to be studied, mostly involving more exotic physics. I've read several papers talking about how dark matter could actually influence the lithium-7 capture and destruction of it in the Big Bang. So then that's it. I just want to thank my collaborators, particularly Dan Bardian, John Schreiner helped me do a lot of the analysis, and my advisor, Jolie, over in the corner. So OK, that's it. Thank you.